Welcome back, everybody. This is part 2 of electrons and atoms. In this video, we're going to be reviewing the energy levels from the first videos, and then we're also going to be talking about how to write electron configurations. Please make sure that you pause and rewind and listen as many times as you need to understand how to write these electron configurations. That's going to be very important. So let's go ahead and discuss some of the characteristics of each energy level. The first energy level only has an s orbital. Remember, the s orbital is the circle shape, and so it only has 2 electrons in it. And so the way that we would write this is a little funky. We would write it as 1s, and then it's like a superscript here, 1s2. So principal energy level 1 with an s sublevel, and in that s sublevel there are 2 electrons. In the second energy level, there's an s and a p orbital. So again, we can have 2 electrons in the s orbital, and we can have 6 in the p orbital. Now, in case you're wondering why this is, remember, each orbital only holds 2 electrons, but in the s, it's just a circle shape. There was only one axis, there wasn't even on an axis. But if we had the p, which was the dumbbell shape, there's the period bell going off. We have a dumbbell shape. It could be on the x-axis, it could be on the y-axis, or it can be on the z-axis. That's supposed to be at an angle. So there would be 2 here, and 2 here. So there would be 6 electrons in all. So the way that we would write this one is we would write it as 2s2, because the second energy, s sublevel, 2 electrons, 2p6. We're still in that second energy level, but now we're talking about the p dumbbell orbitals and 6 electrons in total. So 2, 2, and 2 make 6. The third energy level has s, p, and d orbitals. So we have circular, dumbbell, and then the double dumbbell orbitals. And so there's again going to be 2 electrons in the s orbital, 6 in the p, and 10 in the d orbital. So the way that we would write this one is 3s2, 3p6, 3d10. So if we were to total this up, 2 plus 2 plus 6 plus 10, that's 18. So there's a total of 18 electrons in this third energy level. The fourth energy level has an s, p, d, and f orbitals. Again, 2, 6, 10, and then there's 14 in the f suborbital. So the way that we would write this one is 4s2, 4p6, 4d10, 4f14. So again, if we were to add up all these 18 plus 14, this gives us a total of 32 electrons in our fourth energy level. Now, when we talk about filling up these energy levels, it's pretty consistent up until the fourth energy level. Then it gets a little crazy. So some orbitals do not fill up in a neat order. We're going to talk about that. Some of these energy levels overlap. Okay, some of these levels, like the 1s, the 2s, 3s, overlap. But the biggest rule is that we fill the lowest energy level first. So the lowest energy fill first, and so we'll see what this means. So our out question here, which is normally we would do in class, I just want to do it in this video, is how do electrons move from one principal energy level to another? So remember, if they're in the lowest energy level, let's just say this is 1s, then they're going to have a low energy. So we might call this the ground state. But if I add energy to this, then maybe it can move to the 2s energy state, and we would call this the excited state. So we had to add energy in order to move from the first level to the second level. So energy has to be added to move further away from the nucleus. It needs this energy to move to a higher energy level. So here in the second section, we're going to be talking about more specific arrangements and how scientists write those arrangements, and we call those arrangements electron configurations for each atom. And then we're going to talk about why some of these electron configurations are different than those predicted by this thing we're going to talk about called the Aufbau principle. I'm sure there's a test question or two on this. So here our end question would be, which parts of the Bohr model did we keep? We kept, remember, this idea of these principal energy levels starting off close to the nucleus, then further away from the nucleus. But again, the things that we revised is, remember, now these orbitals are not just plain old circles. Now we do have circles, but we also have dumbbell shapes. We have the double dumbbell shapes. We have those ones that had like the donuts around them. So the placement or the location where we might find these electrons is not as spherical as we once thought according to Bohr's model. Okay, so here is an example of an off-Baugh diagram. So I hope you can kind of see this. It says increasing energy over here. So as you move up, you're increasing the energy. So down here, just a second ago, I said if you're at 1s, you're at the lowest state possible. So 1s is lower state. You might, if you had an electron from here, move up, we'd say it was moving up into an excited state. So we have off-Baugh is German for building up. So this off-Baugh principle here tells us about the arrangement of various orbitals around the nuclei. There's 3 rules. There's this off-Baugh or building up principle. So electrons enter the lowest energy level first. So they're always going to start off in the 1s energy level. Then they'll always go to 2s, 2p, 3s, and it gets a little more complicated after that. This causes difficulties because of the overlap in energy levels from the diagram. And we'll see this in the next section. The next rule or thing that you want to follow principle is this Pauli exclusion rule. So at most 2 electrons are per orbital because they have different spins. So here is Wolfgang Pauli. He came up with the Pauli exclusion principle. And again, it says that no 2 electrons in an atom can have the same 4 quantum numbers. So to show the different directions of spin, a pair of orbitals is written as, you guys can see the up arrow here. Sorry about all these bells, guys, but I had to get this video done before the school ended today. Okay, so you can see these arrows here. So this one is that we generally say clockwise, and this one's spinning counterclockwise. Sometimes you'll see me get lazy, and it's not just me, it's my chemistry professors. And are you seeing how it's kind of like a half arrow there? Sometimes we'll also write the half arrows. You might see that in a textbook or in other tutorials online. So each electron in an atom has a unique set of 4 quantum numbers which describe it, and we've already gone over these. Our principal number, which tells us our energy level, our angular, which tells us what sublevel it's at, our magnetic one, which tells us which direction is it pointing. Think of like a needle and a compass, magnet. And then we have the spin, which direction is it spinning. So the last rule that we're going to need in order to write electron configurations is Hunds Rule. And so Hunds Rule says that when electrons occupy orbitals of equal energy, they don't pair up until they have to. So the idea here is if we had, let's say 3 bedrooms in a house, and I'm just going to draw 3 boxes to represent the 3 bedrooms, but let's say we had 4 kids. Well, we wouldn't put all 4 kids in the same room. We would put one in one room, another in another room, and another in another room. And then if we had to pair up a set of kids, we'd put them here. Then if we had another kid, we'd pair them up in the next room, and then in the next room. So the idea here is if in total we ended up with, I don't know, 6 kids, we wouldn't put all 6 in one room. We'd want to spread them out along the way, and you'll see that in the next slide. Okay, so the first diagram that we are going to make is for phosphorus. And so when we look at phosphorus, it has 15 electrons because the atomic number is 15. So the way we're going to plop the first 2 electrons in is they're going to go into the lowest energy level. So if we look at this diagram, okay, we have increasing energy here. So the lowest energy is down here at 1s. So remember, each box can only hold 2 electrons. Each sub-level can only hold, suborbital can only hold 2 electrons. Here in the next slide, if we already got rid of 2 on the last slide, the next energy level that we need to fill in is 2s because this is the next lowest, so we put 2 more. So if we started off with 15 electrons, now we've got 4, now we have 11 more electrons that we need to plug in. So the question is, where do we put the next set of electrons? I'm hoping that you say we're going to put them in this energy level, the 2p, because it's the next highest energy level. And yes, that's exactly where we put them. Notice how we filled them in. There's 6 electrons in all there. So if I had 6 plus now 2 and 4, that's 10. So if I have 15 electrons minus 10, this gives me 5 more electrons. Now the question is, where do the next ones go? I'm hoping you say that we're going to plug 2 in here to the 3s orbital. And yes, we did. So only 3 more electrons to plug in. And the next question is, well, where do the next 3 go? Well, we're going to plug them in here because it's the next highest energy level. But remember Hunds Rule, it stated that you don't want to put them all in the same box. So I'm going to put one there, one there, one there. So each electron wants to have their own room. And yes, so it says the last 3 electrons go in the 3p orbitals. They each go into separate shapes per Hunds Rule. We do say that now that there's 3 unpaired electrons because notice they're just by themselves in each room, so we consider that to be unpaired. So the way that we would write this electron configuration for phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. So if we look here, there's 2 electrons in the 1s, 2 electrons in the s2, 6 in the 2p, 2 in the 3s, and in the last one there's only 3 electrons up here, so that's why it's just 3p3. Now, here's a good example of how you should write these, and sometimes this is known as the empty bus rule. So as I said a second ago, each kid wants to have their own room. So over here you can see that they drew the electrons like this and left one bus seat or one room empty. But in reality, remember, you start off with the first box, put one in the second box, one in the third box, and then you come and fill the first box again. That's the correct way to fill these diagrams out. Here's just another example of an orbital diagram. So oxygen has 8 electrons. You can see we put 2 in the 1s, 2 in the 2s, and then we put 4 in the 2p. So 2 plus 2 plus 4 is 8. So we have our 8 electrons. So the way that we would write this electron configuration is 1s2, 2s2, 2p4. And I prefer to write these as superscripts. So do you see how like this number here is like written smaller, it's up higher. So 2p4. So that's how we would write that electron configuration for oxygen. Remember, one of the things that I said was that atoms are happy when they have full valence shells. So that's kind of the same idea here, is if we have full orbitals, this is the absolute best and most stable situation for an atom. However, if I can't have a full filled orbital, a half filled orbital is the next best. This makes them more stable than having some in one orbital, some in another orbital. So this will change the filling order. So we're going to see some of those examples here. So tomorrow in class, we're going to go ahead and learn how to write a configuration for each element on the periodic table. We are going to see some examples where this change to filling occurs. Please make sure you write down any questions that you have from tonight's video.